Hello everyone, welcome to week 2 of this course. So in this week we will discuss deep learning essentials after having discussed the NLP fundamentals in the previous week. And this lecture I will start with supervised learning. So these are the concepts that we will cover, what is supervised learning, and we will take example of 1D linear regression. So let's see the terminologies first. So we have heard about AI, ML as some sort of synonyms, but what is the overall perspective and where do they stand? So when we talk about AI, it deals with building systems that simulate some sort of intelligent behavior. Now this behavior may not always come from machine learning. So for example, there are a lot of approaches including logic, search, probabilistic reasoning that can give you intelligent behavior. So for example, if you know when was the first time a computer program defeated chess grandmaster. So 1997. So this is a deep blue system, and this was built essentially using the knowledge of the chess. Okay, so didn't have much machine learning and other kind of concepts involved. Now, when we come to machine learning, right, you can think of it as a subset of AI. So there are some techniques of AI that are part of that are machine learning. Now, what is that? So in machine learning, you try to make decisions, or you learn how to make decisions by fitting mathematical models to observed data. So you have some observed data, you fit some mathematical models, and that's how you make decisions. Okay, and this is incorrectly almost synonymous with AI. So what is important is that you have observed data, and we are fitting some mathematical model. Now these mathematical models are just fitting the data, they may not always explain the behavior as it happens, right, in the real world. So they are just approximations, this mathematical models. So even machine learning, you can divide into supervised, unsupervised, and RL part. So for example, what's the difference between supervised and unsupervised? That becomes very clear. So in unsupervised learning, you do not have the output labels, you only have the input data. So you only have the input data, so you are constructing a model from input without corresponding output labels. So you can just use your input data to create models. On the other hand, in supervised model, you will have both input data and output label, and you learn a mapping from input to output, right. So here the model only learns to represent the input data, where it learns a mapping from input to output data. Right. Now, how is RL different? So RL is slightly different concept, because rather than having a fixed set of input and output space, you are making continuous decisions, and you are actually deployed in an environment where you can take certain actions and you can get some reward from the environment, and accordingly you will have to choose policy that maximizes your reward. Okay. So you choose actions that lead to high reward, and this happens when you deploy the agent in the real environment. So these are typically three different domains in machine learning, and deep neural networks contribute to each of these. Now let's now discuss more on the supervised learning part, because that will be essential for this course. So in supervised learning, as we said, we define a mapping from input to output, and so that means you give me any input, I will give you corresponding output, right. So that mapping has to be there. So how do you learn this mapping? So this mapping has to be learned by a given paired input to output data examples. So you would have a lot of data examples of input and output, and from that you will learn this particular mapping. So let's take some examples of what kind of mappings can I really get, right. So we'll take some different kind of examples. So first one is very common. So where you are given some information about an apartment, that it is 6,000 square feet, 4 bedrooms, previously sold for $235,000 in 2005. It has 1 parking spot, right? And what is your task? Predict the price. So its price is $340,000 as of now, right? So it's a real world problem that maybe you want to put this apartment on a website and you want to know what is a good price I should put for this apartment. Now, given this real world input and output, what do we do in supervised learning? We convert them into some form that a model can understand. So you see, now I am converting everything to some numbers. So I am taking the 6,000, 4, 235, 2005 and 1, putting that as numbers as my input, and my output is 340, right? And inside I will have a machinery, a model that will map this input to this output. So this function from this 5-dimension input to a single dimension output is what I am learning in this supervised learning model, right? And then to the model, its real world consequences of not much importance. So we know that whenever it gives me 340, it means $340,000 is the predicted price, or whenever I give 6,000 as the input, that means square feet, the area of the apartment, right? So this is what I know, but to the model it does not matter. So model takes this input and produces an output, right, by fitting a mathematical model. So, and this is typically a regression problem where you are predicting one particular value, and you can use something like a fully connected network, right, for doing this problem. Now let's look at another problem, another real world problem. So you are given a review from a particular hotel restaurant, and your task is to do sentiment analysis, that is whether it is positive or negative, and let's say this is only positive or negative, so the probabilities for these will add up to 1. Okay. So, and now the model is taking this real input and converting into some numbers, right, and this is the input to the model, and the output is a distribution. So 0.0 to 0.98 add to 1, and this distribution tells us that the model predicts the probability to be negative. So this is a binary classification task. You are classifying into positive and negative classes, and one can use models like RNNs and transformer network for solving this, right? And we will come to that. Now what may be these indices? You can think over it, but this will be like the vocabulary. Think of it like the indices in the vocabulary for these words. Okay. Another example where you are given an image as the real world input, and your task is to classify among the possible objects, right. So like this is a bicycle, right. So again you have to take this real world input, and pixel by pixel you will take the RGB values, RGB, right, and this is fed to the model that predicts the probability distribution for the output, right. So because there are multiple classes, that's a multi-class classification problem, and a model can be like convolutional network that can be used for this. Now you can do translation where your input is in one language, output in another language, right, and again you have to convert this input to some form model can understand, and output in a form that model can output, and then interpret it using your real world, your final real world output. So you see what the input can be variegated. It can have a sentence, an image, or whatever. Even the output can be variegated. It can have a structure in the output also, like here you have the complete translation in the other language in the output. Another example, image captioning. So where you are given a particular image, so you can now again represent them using RGB, and the model will output the particular caption for this, right. So you will simply output the index of the word that you want to put in the caption one by one, and that is what will be the caption generated by the system. And of course, you can use a combination of CNN, LSTM sort of architecture or transformer architecture for doing this. So these are the various examples that tell you certain important concepts about supervised machine learning. So when we talk about supervised machine learning, there is always a meaningful real world input, right? So there is something meaningful that you are doing in the real world. It can be a sentence, an image, or whatever. Now this input will be encoded as a vector of numbers. It forms the model input, and the model maps this input to an output vector. It can also be a scalar vector matrix. And now this output vector will be translated back to a meaningful real world prediction, right? So there is a meaningful real world input and a meaningful real world prediction. In between, I have the whole jugglery of the model. That is mathematical model that takes mathematical input, mathematical output, right? So this is what we typically do in deep learning, that how do you, what kind of different models that you can create that will take an input, a mathematical input, and convert into another mathematical output. So this is what we are doing in supervised learning model. We map from one or more inputs to one or more outputs. Now whatever I am learning a model, it is a mathematical equation that converts the input to the output. So take an example, like your input is the age and the mileage of a second hand Toyota car, and output is the estimated price of the car. Given the age of the car and the mileage, you can estimate the price of the car. Now what would happen in this case? So you would say, I will, given these inputs, I'll have an equation that will take any particular age and mileage and give me an estimate of the price, right? It's an equation, something like 5 times age, right, or maybe 5 times 1 by age, because if age is high, the price will be low, and mileage, if mileage is high, so something like 10 times mileage, and this gives me the price in some quantity, right, something like that. So you are having an equation in terms of the input and predicting the output. But now how do I come up with these equations, right? So that's when we start. But let's say we have this equation. So what we can do? So once we have the equation, so we can compute the output from the input. So once we have the equation, you give me any input, I can get what is the output, and this is what is called the inference. So that's the difference between inference and training part of the model. So in the training part, the parameters of the model are not known. Inference part, I know the model equation, all the parameters are known, and I can simply compute the output given the input. Okay. So that's where comes the training part also. So inference part, your model is completely known, and you can simply, given the input, you can find the output. But how do you find the optimal parameters? What are the best equation? So for that, training is required. Okay. So coming back, so rather than saying model is a mathematical equation, we say when we start, model is a family of equations. So I have various possible equations that can actually be true, that may actually be correct. I don't know which one works best, but then through training, I try to fix on one particular equation. So training a model means finding parameters that will predict the outputs well from the inputs for a training data set. So you are given a training data set of input output pairs, and I want to find out those parameters. So in this family of equation, one equation, that means finding a specific set of parameters that will predict the outputs very well from the input. Okay. Among all possible equations, this equation will predict it very well. Okay. So coming back, so let's say just notation. So you have age and mileage as the input. So it's a vector. So you can write as boldface, and output is a single scalar, say price, and you have a model function of the input. Y is a function of this x. Now what characterizes a model? So model has parameters, and these parameters are to be known. I mean, we have to learn what are the best values of these parameters. So whenever I say y is equal to f x, so it's actually f x and phi, because the model will take the input and only through its parameters will it give you the y, right. So now how do I know whether a given set of parameters fits the data well or not? So for that I have to have a training data. Let's say I have I pairs of input output examples x I y I. So I'll define something called a fit using a loss function. So my loss function depends on, so what is happening, you have I data points x1 y1 x2 y2 up to x I y I. So I have I data points, and now see what is happening, you have a model that is using parameters phi. It takes the input x and gives you output y hat, right. So we also call it f of x I and phi, right. So I need to see how good is this f x I y, right. So how close it is compared to real output. So that's why I define a fit or a loss, saying fine, in terms of the parameters and the model and the all the inputs, how close are the model prediction f x phi to the ground truths, okay, for each of these I data points, or in short we also call it L phi, the loss in terms of the parameters, and it will simply give you a scalar, like for the entire training data set. Now the loss will be low when the model fits better. It will be high when the model does not fit well, right. So it's smaller when the model maps input to output better. So that's the essential for the loss function. Okay. So yeah, so L phi will return a scalar that is smaller when the model maps input to the output in much better manner. And my task is to find the parameters that minimize this loss. So I want among all the possible parameters. So this is what I mean by a family of equations. So each of this possible parameter set can give me a loss. I want to find out that parameter that gives me the minimum loss. So I want to minimize the loss. And that's how the training fixes one particular equation, that this is the parameter that I need. And once I fix this parameter through training, I use that directly for inference. Okay. Now what happens at the testing time? So you simply run it on a separate test data set of input output pairs and see how well it does generalizes on new data. So you already have the model. Now given the input, predict output and compare the loss again and see if the output loss is very similar to the input, the test loss is very similar to the training loss, then it typically generalizes. Okay. So let's take an example. So you have 1D linear regression model. So you say y is function of x and phi, where phi are the parameters and x is the input, right. And let's say because I have a single scalar as input, so x is the only input, so the model can be phi naught plus phi 1 x here, right. So this is a simple you have one scalar input and one scalar output. So phi naught plus phi 1 x, right. Equation of a line y is equal to mx plus c, and it has two parameters, phi naught phi 1. So phi 1 is the slope and phi naught is the offset, right, the y offset. Now So, these are my parameters, this is my model. Now, let us see on different values of phi naught, phi 1 how this equation looks like, how does this model look like. So, it is a simple line, right. So, if I take phi naught is equal to 0 and phi 1 is equal to 1, y upside is 0, I will start here, and phi 1 slope is 1. So, I just keep on going in this direction, right. So, this line I get. Phi naught is equal to 1, so that means I start with y outside of 1, and phi 1 is minus 0.4, so it is a negative slope, I go here. Phi naught is equal to 1.2, slightly higher, and slope is there but little less, so I go like that. So, there are three different instantiations of phi naught and phi 1, and we are giving you three different equations. So, this is a family, right. So, it is a family of equations that you got. Now, you have to select which one is the best. Now, how would you know which one is the best right now? Right now, you can't say, because unless I show you the data, right, which one of these fits the data well, I cannot say which of these three is a better model, right. They all are valid equations as per this linear regression, but which one would work best for you, you do not know till now. So, let us then get the data, right. So, let us say we have the data now. So, you have some points. So, you know this point. So, here this is the x value, this is the y value, and so on, right. This is the x, this is the y. You are given this particular data. Now, once you have this data, now I can go back and see among these three things that I discussed, which one fits this data well, right. But for that, I have to define something called a loss function, right. So, my f x I phi is phi naught plus phi 1x, right, and y is my actual output. So, one way I can define my loss is the mean square loss, that is phi naught plus phi 1 x I minus y I square, and sum it over all the I data points, that is the mean square error. So, not done the mean square error, mean squared error, right, or least square loss function. So, I can use that, right. So, now given this formulation of loss function, I can see which of these three values of phi naught, phi 1 actually fits the data better, right. So, let us say this value phi naught is equal to 0.4, phi 1 is equal to 0.2, right. So, this is the line, and you see it has some problem with each of the data point, and I mean the loss is very high, 7.11, does not look like a good fit, right. So, let us try another value, say 1.6 and minus 0.8. So, now it is not monotonous, but the losses are still very high, like in two different directions, this and this are different directions, but they are very high losses, and overall loss is even higher than the last time, 10.22. But then I use a third value 0.84 and 0.5, and I see now it fits reasonably well. So, now some points are very close on this line, and some are not too far, and the loss is just 0.19. Okay. So, among these three particular possibilities, this one looks the best. Now, I can also typically we visualize this using a loss curve also. So, I am showing two different ways of visualizing the loss curve, loss function. So, on the left hand side, what you are seeing, so you are plotting the intercept phi naught, slope phi 1 on the x and y axis, and the g axis you have the loss. So, this means a very high loss, and somewhere here you have very low loss, right. So, if the dark regions are typically loss is low. So, and this is like in 3D, this is a 3D plot. So, where you can see that the some values are giving you very high loss, but some values are very good, like this value is very good, giving you very close to 0. Right. Now, the same loss function, the loss curve, you can also visualize using a contour map. So, in the contour map, when you see the lines, so these lines are like when you cut this loss surface, right. So, like for example, so this is 10, right, this value is 10 here. So, now if you cut it along this line, right, this entire surface, if you cut along this line where the loss is 10, So, whatever points you will get, everywhere the loss will be 10, right. So, that is what it means. So, along this line the loss remains constant. So, along these contours the loss remains constant, right. So, that is what is the interpretation, and the bright spots are one where the loss is high, and the dark spots are one where the loss is small. So, you want to achieve this particular position, right. The question is, how do we do that, right. So, the way we achieve this is known as gradient descent. So, what would happen? You start with some initial values of phi naught and phi 1. Let us say I start here some phi naught and some phi 1, right, and this is the corresponding value. Now, you compute the loss, you compute the gradient here in the negative direction of gradient, you keep on making progress, take some step, you go to position 1, that is here, and you see there is a better fit. Again you move position 2, better fit 3, 4, and 4 gives a very good fit already, right. So, in gradient descent you start with some initial random point in this loss curvature, and then you start traversing the way to the point where the loss will become very small. So, there are some possible objections that may have, like why are we going through gradient descent? We can always fit this line model in the closed form. Yes, but you cannot do it for more complex models, right. This is possible for linear regression, but you cannot do it for more complex models that you will see. And one can say, okay, we can also try all possible phi naught phi 1 combination with some grid search. You can do grid search and say which one works best. It is okay because you have only 2 parameters, but what about having millions of parameters, like models like GPT-3 have 175 billion parameters. So, how would you try out all possible combinations, right. So, that is why we use a very standard procedure of gradient descent. And yeah, I mean, once you have the parameters, what you do, you will test with different set of paired input output data. So, your test time you will have a very separate set that is held out. So, it is a held out set, it is never shown during training. You measure the performance, you can use the same least square error loss, and if that test loss comes out to be very close to training, it's typically mean that the model is generalizing well, right. But it may not always generalize well. So, what may happen, you may choose a very simple model, right. So, in that case it will not generalize well. You may choose a very complex model, like you try to fit it perfectly to the data, but that would mean that it will not generalize, it will be like overfitting. So, you may run into like too simple versus too complex models as well, right. So yeah, so this for this week we would be focusing on this book, Understanding Deep Learning. So, whatever I covered today, you can read more about it from chapters 1 and 2, and we will continue from here in the next lecture. Thank you.